Hi everybody, Physics Ninja here. Today I want to look at problems related to the escape velocity. I'll do 3 problems. First problem, how do we calculate the escape velocity off the surface of a planet that has a certain mass? Second problem, what happens if I launch something with a speed that's a little bit less than that escape velocity? How high does it go before it falls back? Number 3, what happens if I launch something with a speed greater than the escape velocity? What happens when we're very, very far away from that object, from the planet? In addition to that, we're going to look at how we interpret these results on energy versus distance diagrams, similar to the one I'm showing you here. Okay, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. Leave your comments and questions down below. I'll try to get back to you as quickly as possible. Okay, let's get started. All right, here's problem 1. We want to calculate the escape velocity off the surface of the Earth. All right, so this is the situation. I have the Earth here. It has a mass, m Earth, which is 5.97 times 10 to the 24 kilograms, and I'm a certain distance when I'm on the surface of the Earth, which in this case is 6,371 kilometers from the center. All right, so what do they mean by escape velocity? Escape velocity means I basically want to get really, really, really far away, right? Our rocket here is going to have a mass given as m rocket, and so how do we set this problem up? So the first thing you got to consider is using conservation of energy for this problem. Okay, so again, we don't have any friction anywhere in this problem, so we're going to have conservation of total mechanical energy. So that means at my initial position, which is down over here, versus my final position, the total mechanical energy should be the same. So the way you write that is mechanical energy is kinetic energy initially plus gravitational potential energy when I'm on the surface of the Earth. That has to be equal to the final kinetic energy plus the final gravitational potential energy. Okay, and that's it. This is the total energy. That must be a constant value. So next thing to consider is how do we actually write potential energy for this case? Now, if you solve potential energy problems, sometimes when you're looking at objects on close to the surface of the Earth, we write the potential energy as mgh. Okay, for these types of problems, this is not the right way to do it, okay? Because little g here is not constant. So this is kind of only true if you're close to the surface of the Earth and you take the little g to be roughly 9.8. In that case, you can write potential energy like this, and it's a pretty good approximation. So in this case, we can't use this. And I'll show you why in the next problem. What we have to use here for gravitational potential energy is the more general form, and it looks something like this. Capital G, the mass of the rocket, I'll just call it mr, and then multiplied by the mass of the Earth, and divided by the distance of the object to the center of the Earth. In this case, I'll just call it r right here. Okay, so this is really the equation that we need to use for gravitational potential energy between two masses. Notice it's negative, and that's okay. Okay, the values that we're going to get for gravitational potential energy are only going to be negative. Look what happens when we're very, very far away. We're dividing by the distance here between the objects, between the object and the center of the Earth, for example, in this case. When r becomes very, very big, I divide by a big number. I'm going to get something that tends towards 0 when the distance between the objects is far. Okay, now the term escape velocity simply means that when you're far away, that my final speed is basically going to be equal to 0. So that means that the final kinetic energy is also going to be approximately equal to 0, because I just want to launch something with a speed in such a way that I get really far away, that I escape the gravitational field produced by the Earth. What else? Well, we just talked about gravitational potential energy. For this case here, for escape velocity, it means that r tends toward infinity for the final position. All right, I'm going to have this rocket going very, very far away. So again, if I divide by a large number, it means that my final gravitational potential energy should be equal to 0. So look at this side. The right-hand side of my conservation of energy simplifies, right? 0 plus 0, that's the total energy. Kind of a little bit different than problems when you're so close to the surface of the Earth. All right, so how do we write down the kinetic energy? Well, we're going to have 1/2 the mass of the rocket, mr, and the velocity, I'll call it ve. That'll be my escape velocity, and I have to square it for the kinetic energy. All right, now we're going to substitute what is my initial value of gravitational potential energy. Well, it's the gravitational constant, capital G, the mass of the rocket, multiplied by the mass of the Earth, which I've given to you, okay, and divided by what is that initial position here. Now you got to be careful. It's not zero, right? It's always measured from the center of the Earth to the surface. So in this case here, it's the radius of the Earth. I'll just call it RE for short. All right, now we look at the terms that we may be able to simplify here. We have the mass of the rocket that's in both sides. So actually you could eliminate both of these. All right, the next thing I want to do is I want to solve this problem here for the escape velocity, VE. So I'll bring this term here on the other side and multiply by 2. I'm left with VE squared equals to 2g mass of the Earth divided by radius of the Earth. Okay, the last thing then is you simply take the square root on both sides to get the velocity, the escape velocity rather. And now I could substitute the values in order to calculate this numerically. So we get 2. Big G is 6.67 times 10 to the negative 11. Let me make this a little bit longer. Mass of the Earth I've given you as 5.97 times 10 to the 24. And divided by the radius of the Earth. In this case, now careful, this is given in kilometers, so I'm going to write it in meters. I'll just write in scientific notation. 6.371, this will be times 10 to the 6 meters. Okay, put that in the calculator. At the end of the day, you should get 11,180. This would be calculated in meters per second. All right, typically when we write down the escape velocity, we're going to write things down in kilometers per second, right? You can see it's kind of a nice unit here, and I'll just do rounding here. So I'll say it's approximately 11.2, if I just have 3 significant figures, kilometers per second. Okay, so that is the escape velocity for an object on the surface of the Earth. It's how fast you have to launch it in order for it to never come back. All right, I want to interpret this now using an energy diagram. So I have one here where I'm plotting energy as a function of distance from the center of the Earth. Now, the green curve is my gravitational potential energy at any position, and I start off right here. Right here I'm at the radius of the Earth. So I don't have the curve kind of going inside the Earth. As I go farther away, I divide by a bigger number, but it's always negative, right? So I'm still kind of approaching this line, and when I'm really, really far away, this is really the escape velocity point, right? It's kind of down here, right? When R tends toward infinity, this gravitational potential energy equals to 0. Now remember what we had. We had not only does gravitational potential energy equal to 0 when I'm far away, but also I basically don't want any kinetic energy when I'm far away. So that means that my total mechanical energy then simply has to be equal to 0. So let's go ahead and draw that on the curve. Okay, the total energy, this is the total. For this particular problem, I want the total to be equal to 0. All right, so when I'm kind of going far away, I'd like my kinetic energy to be 0. Now, how would you calculate kinetic energy from this type of diagram? All right, for that one, well, if you think about it, kinetic energy is simply going to be the total, and I have to bring potential energy on the other side. Actually, it ends up just being the difference between these two curves right here. The difference between those two curves is kinetic energy, and kinetic energy is always greater than 0. Okay, remember that. So you notice when I'm on the Earth, when I'm on the surface of the Earth, that difference is the biggest that it's going to be. And when I'm very, very far away at the escape velocity point, right, when R is tending toward infinity, there's basically no kinetic energy down here. Well, let's fix that. Kinetic energy final is the difference between the two. We want that to basically be equal to 0 when I'm far away. Okay, so this is how you would interpret it. So the total energy is a straight line. Potential energy looks like the green curve. And kinetic energy, you can see from the equation up above, if I wanted kinetic energy, I simply bring potential on the other side, and it's E total minus gravitational potential energy. Okay, so it's the difference between those two curves. All right, let's go to the second problem now. All right, here's problem 2. Calculate the maximum height a projectile will reach if it's fired from the surface of the Earth with an initial speed of 8 kilometers per second. Now we notice that this value here is less than my escape velocity. That was 11.2 kilometers per second. So what does that mean? That means I'm not going to make it all the way to the distance equals to infinite distance. Okay, I'm going to only reach a certain height before I fall back down to the ground. Okay, so let's go ahead and write down our energy. So again, the total energy has to be equal to the kinetic plus the potential energy. And that could be evaluated at any point since there's no friction, no air resistance here when I'm leaving the atmosphere. Again, we are simply doing conservation of total mechanical energy. Now, are there any simplifications we can make? Well, you want to calculate the maximum height. So if you think about the maximum height, what happens when I'm at the maximum height? Basically, the speed should be equal to 0, right? So my final kinetic energy for this problem should be equal to 0. All right, so next step, well, let's go ahead and write it. So we know we have initial kinetic energy. We have gravitational potential energy since I'm on the surface of the Earth. So I can write that term, G, mr, mass of the Earth. And initially I'm on the surface of the Earth, so I write RE over here. And my final one, well, let's just write it from the center of the Earth. Let me just pick a different color here. So the rocket is going to be a certain distance, and after I'll calculate the height. But this is going to be my final distance from the center of the Earth. So that means I have final gravitational potential energy. It's mass of the rocket, mass of the Earth, and divided by R final. So my goal now is to find what is this R final value. So we have to do simply a little bit of algebra here. Again, notice that the mass of the rocket appears in all the terms. So that you could simply get rid of. Okay. What I'm going to do now, just to simplify a little bit of the algebra here. Again, I want to get R final by itself. There's a lot of ways to do this, but if I divide through by minus G multiplied by the mass of the Earth, that'll simplify the equation a little bit. Okay, and if I do that, it should look like this. Again, that's going to switch the signs because I'm dividing through by minus GME. So over there, I should be left with this 1 over RE. It's this term. And the second term here, I have to switch the sign. I still have 1 over 2 GME. And I still have the initial velocity squared. Okay, that there at the end should be equal to 1 over RF. All right, let me just go ahead and substitute the values in here. So I have 1 over RF. And then at the end, I can calculate what RF is. So it's 1 divided by the radius of the Earth. Again, 6.371 times 10 to the 6 and minus. So that initial velocity now is 8 kilometers per second. That's 8,000 meters per second. Capital G is 6.67 times 10 to the negative 11. And mass of the Earth, I have it written there, 5.97 times 10 to the 24. Okay, 1 over RF, if I did that correctly, gave me 7.68 times 10 to the negative 8. Again, different ways of doing this. Just flip that around. And at the end, I should get something that's approximately 1.30 times 10 to the 7 meters. Okay, now again, that is the distance from the center of the Earth to the rocket, so be careful with that one. At the end, you want to simply get the height, okay? So you can write an expression for the height as being my value RF that I just calculated minus the radius of the Earth, right? And you could see that from the diagram, right? Because you have that both of those distances. If I sum them, they have to be equal to RF. All right, so our height then at the end, 1.3 times 10 to the 7 minus the radius of the Earth. Radius of the Earth, 6.37 times 10 to the 6 meters. My final height, 6.7 times 10 to the 6 meters. Okay, so that's how you would solve for this height. All right, let's go to the final problem. All right, for problem 3, a projectile is fired with an initial speed of 15 kilometers per second. We want to find the speed now when it's very, very far away from the Earth. Okay, so first thing we notice is that this speed that I'm launching it with is 15 kilometers per second. That's greater than my escape velocity for this Earth. So that basically means that my final velocity is going to be very, very far away, right? I'm going to be able to escape the gravitational field of the Earth if I launch something with this speed. So again, we consider conservation of energy. We have initial kinetic plus initial potential because I'm starting on the Earth. What else? Must be equal to K final and plus U final. Now again, there's a simplification that happens because we're considering the point when I'm very far away. So forget about the gravitational potential energy. I'm going to be really, really far away. So that means I'm going to have some kinetic energy left over once I'm really far away. So we can use that to calculate its final speed right here. Right now, it's kind of the goal of the question. So let's go ahead and do a little bit more algebra. So we have mass rocket, V initial squared, minus G mass rocket, mass of the Earth, over my initial position. I'm starting at the surface of the Earth. This here must be equal to 1/2 mass rocket, the final velocity, final speed squared. All right, like with all the other cases, mass of the rocket appears in all the terms. We can divide through by mass of the rocket. Now we're going to do a little bit of algebra. We want to get V final. So again, I have a 1/2 term. I could eliminate that. So you get V final squared equal to, you multiply by 2 everywhere, V initial squared, and minus 2G MERE. Okay. Now, if you think about this term over here, last thing we want to do is simply take the square root. And we're just about done. Take the square root on each side. Here's my expression now. Now we substitute in our values. And guess what we get? Initial velocity was 15. Again, we get 15,000. And minus. Now, this term here, again, 2 times 6.67 times 10 to the negative 11. Let's make this a little bit bigger. Mass of the Earth, 5.97 times 10 to the 24. Over the radius of the Earth, 6.371 times 10 to the 6 meters. That's my expression for V final. All right, V final now in this case gave me approximately 1 times 10 to the 4. That's in meters per second. Again, it's kind of common here just to write things in kilometers per second. So that's approximately 10 kilometers per second, even when I'm far away, right? When R tends toward infinity. All right, now let's go look at everything now on a energy versus distance diagram to make sure we understand the 3 different cases. All right, let's put everything now on this diagram. Now, there's quite a lot going on, but that's okay. Total energy is always kinetic plus potential, and that should be a constant. Okay. Remember, our kinetic is always a 1/2 mv squared, and our potential now is given by my green line, okay, and that's minus G m mass of the Earth in this case divided by the distance. Okay, that's the total energy. All right, now a couple cases that we've considered. First of all, the orange line over here, this was for the escape velocity case, right? This is when my total energy was 0. Because if I looked at my final total energy, I had basically no kinetic. I just got there. And I was very far away, so there was no gravitational potential energy. So that is this case. At any point, you can calculate what is the kinetic energy, right? Because I can write that the kinetic energy is the total minus the gravitational potential energy. Okay, so anywhere on this diagram, I can calculate the difference between the orange line and the green line. That gives me how much kinetic energy I have. For my escape velocity, you can see that those lines, the orange and the green, tend toward each other, so there's no final kinetic energy. Now, problem 2, if you remember problem 2, I launched something with an initial velocity of 8 kilometers per second, right? The initial velocity was less than my escape velocity. So what actually that means here, if I have kinetic energy that is too small initially, it means that my total energy is going to be a negative value. So the way you represent this on the diagram is by the blue curve. Now you can see there is a point where this blue curve intersects the green one. Well, guess what? Remember, the difference between both of these lines is always the kinetic energy, right? That's always the K value. So if they intersect it, it means that the kinetic energy at this point should be equal to 0. And that means this was really what the maximum distance was that I calculated, right? This is basically the value RF. I only get so far before all that energy gets converted into gravitational potential energy. I start with kinetic energy, but after I convert that into gravitational potential energy. Now, the last case, I had a initial velocity that was bigger than the escape velocity. So that is represented by this red line. So my initial speed, let's go ahead and fix that. The initial speed was greater because I had 15 kilometers per second. It was bigger than my escape velocity for the Earth. So that means in this case that the total energy of the system is greater than 0. If you actually substitute it in our values here, we can actually get a number for the total energy, and you'd see that this kinetic energy term is bigger than the gravitational potential energy. So when I take the difference between both of those terms, I get a number that's greater than 0. Now, remember, the kinetic energy is always the difference between both curves. So let's just kind of clean this up a little bit. So if I think about it now, if I plot what the kinetic energy looks like for case 3, there's always a distance. It doesn't matter how far I am, I can always calculate a final kinetic energy. Even if I go all the way to infinity, you can see there's always going to be a difference between those two lines. That means I'm always going to have a final speed. In our case, we had 10 kilometers per second. Okay, so this is kind of how you interpret things on an energy versus distance figure such as this one. Okay, total energy is always represented by straight horizontal lines. Our gravitational potential energy is represented by the green line, and kinetic energy can be calculated as the delta, or the difference between both of those, depending on the situation that you're dealing with. All right, thanks for watching, folks.